what is omega hat in this case? You all know it, you've seen it before. Okay, so let me first say what c dot is. C dot is the translational velocity. Translational velocity, and omega hat is the angular velocity. It's a vector. Okay? And so we've seen that in writing out the Eulerian or spatial velocity, we have come to a form which should be very familiar to us, right? It's the translational velocity plus the angular velocity vector crossed with the position of every point relative to the motion described by this translation. So, in describing this rigid motion, we can do it by picking a point, right, and talking about the translation of that point. We may just choose to parameterize it by saying, okay, it's a translation of this point, right, the translation of this point, plus the rotation of the body about that point that is translating, right? Right, and omega hat is this quantity, right? Omega hat is the angular velocity vector. Okay? So that's a very useful way to think to write out the Eulerian or spatial velocity. What we're going to do now is to take this one step further and see what this implies for the acceleration, right? So now extend this to the Eulerian acceleration. We will start out by recalling that when we talked about the Eulerian acceleration, we said it is equal to the Lagrangian acceleration. Okay? And the idea is that the acceleration of the body is the acceleration of the body. It's just a question of whether we choose to parameterize that motion by the reference position or by the spatial or current position. Okay? They've got to be the same. What that implies is, recalling the relation we had a few slides ago, we have this. Okay? They're the same, except for the fact that we can't use capital X here. We want to parameterize it with little x. Okay? So I am going to, I wrote this capital X only to remind ourselves of the fact that it is there, but I am going to rewrite that capital X as Q transpose X minus C, using the relation we observed from inverting the motion. Okay? And to remind us of that relation, I'm just going to say that this is capital X, the reference position. Okay? What we will do next is work a little with Q double dot. Okay? And I am going to do that by going to the next slide. Okay, so consider Q double dot. I'm going to rewrite it as Q double dot Q transpose Q, and I've done nothing here because Q transpose Q is simply the isotropic second order isotropic tensor, right? Your identity matrix. You can multiply any tensor by it and it leaves the tensor unchanged, right? So that still is just Q double dot on the right hand side. It better be the same, right? Okay, plus Q dot transpose Q minus q dot transpose q. The right hand side is just q double dot, right? Because the last two terms cancel out each other, right? But now observe this. I can write the first two terms, okay, as time derivative of q dot q transpose acting on q, right? Just by the chain rule, right? Partial with respect to time of q dot q transpose gives us the first two terms on the previous line, okay? And then, of course, I have this term, minus q dot. Now, here I'm going to do something else here. I'm going to put in a q transpose q, all right? Q dot transpose q, all right? And in doing so, I'm using the fact that this product is again the second order isotropic tensor, right? Which I have chosen to insert in there, okay? Right, so I'm just putting in other tensors which leave the whole right hand side unchanged, but just give it to me in a more convenient fashion, okay? All right, but then this is just what we decided to write as omega, right? The skew-symmetric tensor, right, on the previous slide or two. And its time rate is just then omega dot q minus, here observe that I have the second term is omega transpose q. All right, why is this? Because q dot q transpose is what we defined as omega, okay? Right? But then omega is skew symmetric. So I can absorb the minus sign here and the transpose here, right? I can combine those two to write this out as omega dot q plus omega q, right? I absorb this minus sign in the omega transpose since omega is skew symmetric, right? I can write that as, I change the sign on this as plus, right? And I get omega. This is because minus omega transpose is omega because it's q, okay? All right, where did all of this come from? We used this back in a x comma time equals c double dot plus q double dot q transpose x minus c from the previous slide, okay? And what we've done here is write out all of this for q double dot, right? All of this comes down to q double dot, okay? We're going to make that substitution, right? And I'll write it here so that we have it, and then we'll take it to the next slide. It's c double dot plus omega dot q transpose x minus c plus omega q transpose x minus c. And observe here that QQ transpose is the second order isotropic tensor there as well as there. Okay? So, putting all of this together, we are going to see that the Eulerian velocity can be written as C double dot plus omega dot x minus c plus omega x minus c. Okay? But then, if omega is q-symmetric, so is omega dot, right? Okay? So that lets us write this out as C double dot plus, here we have omega hat dot. Remember, omega hat is a vector crossed with x minus c plus, here we're going to write out the first omega acting on x minus c as omega hat cross x minus c. Okay? And the second one as omega hat crossed with all of omega hat cross x minus c. Okay? We're done here. Note that again, C double dot is the translational acceleration what is omega hat dot? Think about it. What is omega hat dot? It is the angular acceleration. Okay? And the last term, which is given to us by omega hat cross omega hat cross x minus c, okay, using a property of the cross product applied to a cross product, can be written as omega hat dotted with x minus c, right, which is a scalar multiplying omega hat minus omega hat dotted with omega hat, a scalar multiplying x minus c. Okay? All right? So what we see here is that these two terms give us in total the centripetal acceleration. Okay? This term is the more familiar form of the centripetal acceleration that you've seen. Okay? And there is another contribution to it here. Okay. We are going to stop here for this segment.